Thanks to the organizers for having me here. It's a great pleasure. So it's my first time at ESI. Well, let's say my first time in ESI, but not at ESI, because there was a workshop during COVID, and all this was online, unfortunately. So I was looking forward to coming, and now 5 years later, finally I'm here. So it's very nice to be here. Very nice to see so many familiar faces and get to know some new people. And I have to say, I'm a little bit intimidated by the crowd, because you know this subject very well. And okay, so we have so we made some observations there that may be interesting to one or the other. And so basically, we are concerned with weak solutions for mean curvature flow, and there's somehow a very canonical solution concept on one side, the viscosity solution, and then there's a whole zoo of weak solution concepts on the other side, and I would like to maybe draw some connections, maybe some of which you did not know yet. Okay, so this all this started actually in Bonn, when I gave a lecture series on mean curvature flow, and then I, after returning back from Berkeley, I have to admit that's when I actually really read Evans Sprague, the fourth paper, in full detail, because I did this in my lecture. And this is the big inspiration for this, is this paper by Evans and Sprague, the number 4. Beautiful paper, so I recommend you to read this. And somehow, maybe I want to show you that this is maybe half of the story, but the other half is maybe not so hard. Okay, so I want to maybe start by, maybe for those who don't know mean curvature flow, in the interest of the people talking after me, maybe I'll tell you what mean curvature flow is. So classically, you just give me a nice embedded surface, and then I solve this equation such that the normal velocity is the negative mean curvature. So Shokuk already mentioned this, but let me just explain it once more. So somehow the sign convention here is that v is the velocity, kind of the outward normal velocity, somehow how fast this set, the interior, is growing. So I always think of closed manifolds. So they have an interior, and this interior, if this expands, then I say, well, it's growing, so v is positive. And the mean curvature, right, is just the trace of the second fundamental form. And in the I take the sign convention that convex set, so when this interior here is convex, then this curvature tensor is positive. Okay, so you can write this in coordinates, right? So if I have a parameterization, let's say x, and this, and you can choose a smart parameterization, then you just see is this diffusion equation. So it's like the diffusion equation, but okay, it's vectorial. We don't have to be afraid of this, but we have to be afraid that this Laplacian depends on kind of the coordinates that you had there, and they are, of course, I mean, those are the ones here. I mean, it's of course coordinate independent, but maybe you want to do these computations in coordinates, and you see, well, it's just the diffusion equation, and you would think, well, this is trivial, but of course not, because those coordinates depend on the solution, and in fact, of course, this even kind of, it depends on the geometry of that surface. So yeah, so that's why kind of the solutions can look very nice, very interesting. First thing, right, that spheres shrink and disappear in a point. So they're self-similar, and then you can write down the ODE for the radius. And yeah, so in 2D, Gage and Hamilton and Grayson understood this very well. Huisken understood in higher dimensions also that as long as you're convex, you will shrink, and as you as you disappear and I rescale, it's going to look more and more like a round sphere. So this is one kind of singularity you can get, and in 2D, that's all the. For curves in the plane, embedded curves in the plane, that's the only singularity that you will see. But in higher dimensions, you can see more. So in higher dimensions, of course, you can also take a sphere here. This is, of course, one option, but of course, you can have cylinders and so on. And you can also have singularities after which you want to continue the evolution. So maybe should have put here a long cylinder. If you have a thin neck between two big spheres, you connect them with this thin neck. This thin neck is going to shrink very fast, and it's going to give you pinch off. So there's a singularity here, and that's kind of what you see in lots of kind of free boundary problems or geometric flows. That kind of you will have singularities through which you want to flow, and there should be a canonical way of doing this. And that's maybe the first thing you would do is to say, okay, well, what I'm looking for is not a classical solution, but a weak solution, right? And of course, that's what people did. And kind of so let me put two worlds here. So on the left, I put things that are based on the comparison principle. And on the right, I put things that are based on the gradient flow structure. Okay, so the comparison principle tells you if you have, two surfaces. I mean, they continue here, let's say, but if they're ordered, they remain ordered. And that's kind of if you have two graphs, then you see this is the classical comparison principle for parabolic PDEs. So this one will never be able to catch up. So let's say, and maybe I express this in terms of the interiors. So this is this one here, and one without tilde is everything on this side. And think of them as closed manifolds. So if okay. If they're ordered initially, they remain ordered. So it's a geometric comparison principle. And on the other side, so this is kind of, you need some kind of structure maybe to come up with the solution concept. And here the structure is that it's a gradient flow, steepest descent in an energy landscape, and you can just compute how the area changes. It's equal to this. And then you plug this in, and you see this is the direction of steepest descent if you measure in L2, right? Of course, this L2, I mean, kind of it's not. So we're not talking about a Hilbert space. We're talking about some strange curved space, right, of all, let's say, closed manifolds, and then this is kind of the L2 inner product on kind of whatever your perturbations are. So perturbations of a surface I can identify with normal velocities, right? So, or functions on that surface. Okay, so these two, I mean, they're in itself extremely useful if you want to also talk about classical solutions. So, for example, if you want to prove this pinch-off, I think the most elegant proof I know is by comparing with two other solutions. By maybe putting one big sphere in here and here as well. Putting a torus around here. And so this is Angenand gave this self-similarly shrinking torus that kind of so it shrinks by just scaling. So the mean curvature flow of this torus here is just it shrinks down to this point here. So and and you have this comparison principle that tells you that this white surface is always between those ones. And now you see immediately that if these spheres that I chose initially, if they were chosen big enough, I mean the curvature is then very small, so they shrink very slowly. And of course this torus here it's already disappeared, so you see immediately that there is a singularity that's interesting. Okay, so that's just to show you that kind of at maybe one of the most basic examples that kind of the comparison principle is very useful. And of course, this here always gives you some energy estimate. So that's also, of course, very useful. Okay, so what is the viscosity solution? That's the one here. So that was introduced by Equivalence and Sprague, and independently by Chen, Giga, and Goto. And the idea is the following: if you now that you have this now that you have this comparison principle, you could start with a foliation of space. So you do a foliation by closed manifolds, and then you let each of them flow. And of course, they will remain ordered, so it's going to stay a foliation. And you can, if you started basically with level sets of a function that says that you flow each of these level sets, that should again be a function. And now it's an elementary computation to say what is the PDE for that function. And so if each level set of U has to solve mean curvature flow, then you can see that U has to solve this degenerately parabolic equation. U is equal to U0 at, so this is maybe, let's say we do this in ambient space RD, and at t equal to 0, you say you take these initial conditions. So this here means basically all level sets are mean curvature flows. That's what this equation here says. I put this in quotation marks because somehow, I mean, you see already the obvious problem that you divide here by the length of gradient of U. This is one problem, so that kind of this is not well defined when gradient U is 0. But there's another problem, is that this is not uniformly elliptic, this operator on the right. Right? So there's one direction, and that's exactly the normal direction in which it completely degenerates. There's, of course, clear that the kind of two different level sets don't see each other because both of them do their own thing. They move by mean curvature flow. There's no diffusion between them, just along the surface. Okay. Okay, so that's the solution concept. And you can, how you now define these solutions is by testing from above and below by, smooth functions. And then you say they should satisfy this equation with an inequality. This is how you define viscosity solutions. You still have to be a bit careful with this, but okay, the experts know, and the others, for the others, maybe it doesn't make sense to discuss this in too much length. But basically, you can choose a direction. Basically, you should think. Okay, so this is a beautiful concept, and it gives you unique solutions. So you give me a function, and you give these people a function, and they give you back the unique viscosity solution. Okay, and this is maybe a bit strange if you think of one example, which is if the function that we started off with had a zero level set. So suppose I want to evolve this surface here. So it's, of course, it's a singular surface, but okay. So should be easy enough that we can solve a diffusion equation starting from there, right? So if this is your sigma of 0, it's a cone, and so you should be able to solve the mean curvature flow, and kind of depending on how you define your solutions, it's pretty clear that there's no unique solution starting from there. So more precisely, for example, if you do this on your computer, you will never see this. So this is unstable, and you would get either this connection opens up in this way and it's going very fast away like this, or going very fast out like this. So those are two, symmetric. They are kind of equivalent, these two solutions, in the sense of, I can't say which one is better. So there can't be uniqueness. And so this is what you would expect for somewhat classical solutions starting from there that maybe attain the initial condition just in a weak sense, but otherwise classical. They should look like this. And where maybe you could also say another option is to just stay here, but that's unstable. And what the viscosity solution is doing is it says, well, this thing evolves to a function whose level set will contain all these solutions. So this is one possible solution, sigma 1, let's say. And there's another one, sigma 2 of G. And the viscosity solution is unique. And in fact, it contains all these solutions somehow in this zero level set. So, yeah. Well, wait a moment. So sub and super solutions, well, they're not unique because so you can take a maximal sub solution, you mean, and a minimal super solution. Yeah. But so this thing is also unique. I showed this last week in my lecture. Sorry. So that function is unique. So this is, I'm not saying more than this. I'm just saying this function is unique, and that you can really prove very elementary. With doubling of variables, you can do the comparison principle for weak solutions of this. Viscosity solutions of this. Okay. So let me tell you what the weak solution concepts are here. And the first one was Brachy's, been called Brachy flow later, where he says, okay, this is the central thing here. So I take this as the definition of my solution concept, but he says I want to localize this. Basically, this inequality should hold true for every test function that is non-negative. That's what Brockie said, and it's basically saying that you have this energy dissipation identity at least as an inequality, and you can even localize it, and then of course you get these terms of you get this advective derivative basically of phi, because I mean you're evaluating phi along that surface, right? So the surface may go through the support of phi, for example. Okay. So those who attended Yoshi's class know that there should also be a multiplicity maybe here, but I'll ignore this maybe here. Another concept are distributional solutions. This is due to Laux and Sturzenhecker. And they basically say, well, you can encode both sides of this equation, kind of that, what the normal velocity is and what the mean curvature is, in a distributional sense. So if I take the indicator function of this of the interior, that's going to satisfy the transport equation as you saw it in Sebastian's talk, and so this would be a possible definition of the normal velocity. So the same. And well, the mean curvature, well, it should be the first variation of this energy function, right? So that's the usual thing. So kind of the first variation of the energy. That's kind of what the mean what's the mean curvature. So we assume this. So here the concept is there exists a function such that the first variation can be written as integrating against that function, and the time derivative, you know, that's a measure, and this is a measure, and you have a Radon-Nikodym derivative here. And then you say that these two functions, basically you can say it like this. So kind of, this may be one way of phrasing it. And they have to agree. And basically, these two things together, this would be very natural, and that's basically what Yoshi, in a series of papers, the maybe most important bit was this last part with Struwad, canonical Brockie flows, where you basically say you have these two things. So it's slightly different because you don't get exactly this transport equation, and then there's also these de Giorgi solutions that so this is so it started with Kim and Tonegawa, but then Kim and so you can also try to find a minimal solution concept that at least is consistent with strong solutions, and that's what Sebastian and I did. That we defined these de Giorgi solutions that also just satisfy energy dissipation inequality, but actually just one global one. And the interesting thing is that this one is actually already has all the weak strong uniqueness property, although it's just an inequality and it's just one. Okay, so now I'm omitting lots of other solution concepts, but somehow we all agree on the left-hand side that the viscosity solution is a good notion, I think. And on the right-hand side, there's lots of different kind of attempts of finding a good solution concept. And I want to maybe give you today the message that it's kind of maybe we're all right, that it's kind of, we can reconcile them a little bit, at least in this generic setting. Okay. So let me just show you kind of how you can go from one solution concept to another. And this is maybe somewhat inspired by this work in PDEs, classical PDEs, where you can say that viscosity solutions and weak solutions that are kind of like everything on the right, that they're equivalent in that case. So Ishii did this for linear PDEs. And this is basically what you want to do here, but it's a bit different in this geometric context. And yeah, so we have these different kinds of results. So let me start with theorem 0. 0 not because it's not important, it's very crucial, but it's not mine. So let me just show you this. This is what inspired this whole thing. So this is Evans and Sprague, the fourth paper. So this is in geometric analysis 25, I think. So this was around exactly at the same time as Laux Schulzenhecker's paper, for example, also. And they say, so you need somewhat reasonable initial conditions, but then almost every level set of the viscosity solution is a unit density Brachy flow. So that means that generic level sets of this viscosity solutions, they are one of these ones up there. So it's kind of giving you a connection from this one world to the other, and it's a very nice proof, I think. Then when I did this in my lecture, I also kind of gave the additional thing here that then later Anton Ulrich and I wrote down. It was also here in, I think now it appeared in 25, so 30 years later exactly. So we can say that also almost every level set of the viscosity solution is a distributional solution. So and these two. So this is this is really fundamental, I think, and this is just an observation that you can actually see that kind of you have enough estimates here already to do this. But it's strange that it didn't appear already then, somehow like shortly after. So the idea behind this is the following. So Evans and Sprague. So let's say formally, Evans and Sprague prove this estimate here. So H is the mean curvature of a level set. So it's this here. They can prove this, well, not for the equation itself, but for an approximation. And because they have uniqueness here, yeah, they prove nothing, exactly. No, of course, they prove this is finite. Yeah, they prove this is finite. Yeah, thank you. So L1, sorry, L infinity with values in L1. It's a strange estimate, and I think they comment also and phrase it in a similar way, that kind of you get this strange estimate that does not disintegrate after you disintegrate the level sets to something that just says something about each level set. It says something how these level sets talk to each other. Right? I mean, so kind of there's, if you want to do co-area formula, you put this co-area factor there. And the usual estimate that you get is kind of, if you integrate up the energy identity up there, you get kind of something with an L2 here, but with the area weight, right? So this is a strange estimate. And of course, you need to have a good approximation to do this. And then in the limit, you also get this. So how they do this, because this thing is unique, they can choose their favorite approximation, and for their vanishing viscosity approximation, you can prove exactly such an estimate. It's a beautiful proof. I'm not going to show you today, but so you get an estimate like this, and then still, so I'm doing everything formally here. You can show the following, of course. So this is all formally here, okay. So let me write it as u times. So I integrate by parts. Now if I have an L1 bound here, so this is bounded as measures, and this here converges uniformly when you do an approximation. So you can do a compensated compactness argument here, and you see that when you do your nice approximation, let's say some u epsilon here, you can pass to the limit here, and you can identify what these limits are, and then in the end you can show that this total mass converges, and then also, of course, these measures here converge, or actually, these as functions, but they converge. You don't lose mass. And when I saw this, I thought, okay, well, this is exactly what Laux and Sturzenegger have to assume to get their distributional solutions. It's a very different scheme that they use, of course, but so this allows them to get the Brachy inequality. But if you know the paper by Laux and Sturzenegger from the same year, then you see, well, this is exactly what they need to prove that the tilt excess goes to 0, and so it converges and then goes to 0. So this allows to do both these things. So what you do then, so you have this estimate, so you can get, let's say, an integrated version. So over level sets, integrated version of either the Brachy inequality or the distributional solutions identity. So, and then you disintegrate that. And there's another trick that you can relabel the level sets, and there's kind of some invariance that you can then disintegrate. Almost every level set satisfies this. Okay, so this is the short story of what's behind those papers. And what they do is, in this picture over here, they tell you that you can go from here to there. Okay, so I gave this talk in Pisa this summer, this part of the talk, and I really hope that somebody would ask, well, can you go this way? Okay, so now I can answer this after nobody asked. But in personal conversations, this showed up a couple of times, and basically, we would like to see how you can go back. And if you look at this paper by Ishii, for example, kind of so the point of going back from kind of a variational solution, something that is based on, integration by parts and writing things, in this weak form, how you can go from there to the viscosity solution, something based on the comparison principle. You need to get a comparison principle for these, variational solutions. So that's at the heart of this. So let me first write down what the result is. So this is now in the archive. So we can go back to both of these, and it's somewhat not enough to have just Brachy or just distribution solutions. So I would wish that this would be enough, but Brachy is very central to us. So let me basically say so. So let's say. So I call these two things together. I call this a variational solution. This is So saying that the sets are a distributional solution and their reduced boundary are Brachy flows. And then, so if U0 is well prepared just like this, is as in theorem 1. So there I said just in words that it has to be well prepared, but under the same conditions, any so one parameter family, let me write it in the complicated way, and one parameter family of variational solutions gives rise to the unique viscosity solutions. So when you can stack them, so that means first of all, so for so they foliate space, you get a function, you can construct a function u, x and t, such that u greater than s gives you exactly the omega s, and the u equal to s gives you the sigma s for almost every s. So first of all, it's a function, and then the second thing is this is the unique viscosity solution. Okay, so that tells you that you can go back when you have those two. You can go back here. Okay, in the remaining -1 minute, I'll just tell you kind of the essential thing here is that you can get a comparison principle for kind of variational solutions. And here, kind of, I take this kind of ambivalent term, variational solution, because it's somehow, you can somewhat take your favorite combination of things here. So you need Brachy, and you need something that gives you some regularity in time. Because Brachy has this horrible property in general, that if you give it a ball, kind of a sphere, even then it could say, well, okay, well, your solution is the empty set. Kind of just make everything disappear, that's also a solution. You have no regularity in time, so to say. So you won't have a comparison principle. There's just this very famous avoidance principle that you cannot jump on top of another Brachy flow. But if you want to have a comparison principle, really, you need some. So the most important thing is Brachy's inequality, but then you need something. So this is plus, and this is basically regularity in time. And any of these other solutions, these extra conditions, give you that. And that's maybe a corollary that I'm not going to write down. So it tells you that kind of all these things are the same because so generically these solutions would give you the same answer to kind of what's the solution to running from one leaf in this initial foliation, and the kind of take-home message that I want to give you is that kind of this tells you. You can go forth. So you can go back and then forth again, basically, and then say that kind of if you give me Brachy and something, it's the same as Brachy and something else. So all these solution concepts are somewhat equivalent generically. And okay, so if you have multiplicity, so you have to be maybe more careful. But kind of this is maybe how I view it. So this is the result. So and it's very different to this direction here because you kind of the central goal is to get this comparison principle for these variational solutions. I hope this was of interest for you, and yeah, thanks for your attention.